Good morning, one and all. Today, February 29 is a leap day, which is an extra day added to the calendar to the calendar every year. The extra day added to the February to make a leap year, which is also known as the intercalendar year. So today is the fourth day of our FPP program. Today we have the guest and eminent speaker and a scientist, Dr. K.G. Sankaran, senior scientist, CSIR, Institute of Mineral and Materials Technology, Bhubaneswar, Odisha, India. He completed his bachelor degree from Madras University with the university rank holder and masters at Anna University in Material Science, India. And he has he obtained his PhD from the Taiwan National Tsinghua University. After that, he joined as a research associate in SICRI from 2007 to 9. He has some postdoctoral experience from 2013 to 14 in the same lab Taiwan. Later that, in 2014 to 19, he has the various positions in Institute of Material Research, Belgium. 2014-15, he obtained his Marie Curie Postdoctoral Fellowship Award. And 2015 to 18, he has the Postdoctoral Research Award from the University Institute of Material Research, Belgium. In 2018 to 19, he the Postdoctoral Research Fellowship from the University Institute of Material Research, Belgium. He obtained the various fundings from the CSIR, SARB Startup the Research Grant, and CSIR CAS Mobility Plus Research Grant, Bilateral Fellowship Grant, and he also obtained the grants from the UGC CAC DSR. He also received the grants from the SARB Accelerated Wing Scheme. He authored the research papers more than 100 plus. Out of 100 papers, he has 45 papers as a first author. His H index is 24, and the total number of citation as per the Web of Science will be 1757. He has received so many awards like Excellent Poster Presentation Award from NTTNC Taiwan, and research proposal selected twice for HZB Berlin, and he has selected by FWO, and he has obtained the research grant from the FWO, and he has received the Best Oral Presentation Award. He has obtained his Outstanding PhD Scholarship Award from the National Tsinghua University, and he has a Rank Holder Award from Madras University. He has a various experience with the thin film deposition, microwave plasma chemical vapor deposition, and nanostructure fabrication. He has experience with the cold probe techniques and the electrochemical auto lab measurement. He has some wide range of expertise in the material science field. Now I invite the sir to deliver a lecture. Sir, thank you, sir.
Thank you, sir, for your kind introduction. Sir, shall I share my screen?
Yes, sir, please, sir.
Yes, sir. Sir, is my screen visible?
Yes, sir. It just moves, sir.
Is moving, sir?
It is moving, sir. Okay, sir.
Okay, sir. So, good morning, everyone, and thanks to the organizers of this faculty development program for giving me an opportunity to present my works here. So, I am Sankaran, a senior scientist from CSIR Institute of Minerals and Materials Technology, located in Bhubaneswar. So, today I am going to talk about the fabrication of the diamond electrodes for electronics and the energy applications. Basically, diamond is an insulating material, but for electronics and the energy, it should be conducting. So the work that we have carried out here, which based on the how the diamond is electrically conducting, we have fabricated, and the applications we have focused here electronics and the energy. So before going to my talk, I would like to introduce about the CSIR, Institute of Minerals and Materials Technology. So this is the main building, which this institute located at the middle of the Bhubaneswar, and it's very green and clean environment. So here I have we are working with 8 departments. advanced metal technology, design and project engineering, mineral processing, central characterization, and hydrometallurgy, environment sustainability department. Among these department, I am working in the advanced material technology department. Here are the research activities that we are focusing in the IMMT, that we are focusing on the plasma processing of minerals, waste and special materials, metals and alloy making. We are also having a team working on the carbide, oxide and nitride powders. And then we have a preparation unit for the electronic and the high pure materials. We have very good characterization facilities in our AMT department, as well as we have a central characterization department which involves all the spectroscopies as well as the microscopic units, to have a very good infrastructure in IMMT to carry out a very a fruitful research for all kind of minerals and materials, for any kind of devices. So here is the outline of my work. Today I'll discuss about what is diamond and what are the fabrication process involved in the synthetic diamond process, and how we are making the electrically conducting diamond. We call it as a diamond hybrids. Then focusing on the electronic applications in terms of field electron emission, microplasma illumination, and in the energy we focus on the electrochemical supercapacitors. And finally I summarize my talk. Sir, I hope my slides are moving. Thank you, sir. So, as we all know that this is the carbon material with the 2s2p, 2p2 configurations, and these are the different states of the carbon, free states and the combined states. I'm not going to talk about the inorganic and organic phase of the carbon. Basically, with the crystalline and the amorphous based materials, and particularly diamond, and some places it combines with the graphene related diamond and graphene hybrids to make it electrically conducting. So how the diamond, before going to talking about the diamond, I want to first tell something about the carbon, the specialty of the carbon. Here are the allotropes of carbon. You can see the sp3, which is the hardest known material, that is the diamond, having the bonding of covalent bonding. Then you come to the sp2, that is the graphite, which is a layered structure in having a van der Waals kind of bonding. Then it is C60, this is a buckyball like structures. Then C70 graphene. Then C70 is here carbon nanotubes. Then it's complex with the 2D materials like the graphene. Now people are talking about the graphidine and further other allotropes of carbon. So the specialty of the carbon is the only one same atom which has different properties. That properties that are depends on the orientation and the hybridization of this carbon material. So this is the unique features of this carbon, which having a different properties that depends on the orientation and the hybridization. So now coming to the diamond, as we all know that it's a precious stone in the jewelry, and people are very much fond about this one to utilize in their jewelry things. But I'm not going to talk about this phase of the diamond. There are different phases of the diamond which can utilize for various applications. Some of the applications I have focused here, I have shown here is that it can use for the grinding, polishing, and hard coatings on drill bits, cutting tools, and dicing jaws. And we can use the diamond for the high power electronics because thermal conductivity is very good, heat sinks and radiation detectors, and it is very chemically inert in nature. So we can, it is inert to acid, bases, and the other chemicals. So here some of the crystal structure of the diamond. It's a face-centered cubic, and the latest constant is 3.5 Armstrong, and it has a very good atomic density, over like 10 power 23 per centimeter cube. So based on these properties, diamond is having the covalent bonding, which having a very hardest nature of this hardest known material. And these are the some of the basic properties of the diamond. The hardness I mentioned like a 10 ohm scale, and Young's modulus is 10 power 12 Newton per meter square. And you can see the coming to the electronic application, the band gap is too high. It's a wide band gap material, and the resistivity is more than 10 power 16 ohm centimeter. So it is very much difficult to make the diamond electrically conducting. So that is the task people are now carrying out to make the electrically conducting diamond. So before going to the synthetic diamond, how people are manufacturing, it is better to know about how natural diamonds are made, or how it is created. So it basically needs two process that parameters, that is according to the pressure and the temperature, we can get the natural diamond by 4 processes like the deep source eruption, asteroid impact, meteorite fall, and the subduction zone. So the 2 parameters required for the natural diamond is the temperature and the pressure. And if you want to know more about the formation of the natural diamonds, there are some natural mines in Africa, and this is a Hollywood movie. You can watch this movie that shows the value of the diamond, how people in Africa suffers to get a small carat of diamond, which goes for various applications and mainly for the jewelry base. So the value comes from that, how people are suffering in the mines. So that the natural diamond is too expensive. So the researchers made efforts to make artificial diamond. So how artificial diamond is created? Um, so when you want to create the artificial diamond, people tried with various methods. One of the method is the plasma based synthesis. So I want to touch up something with the basic of the plasma. So we know about the major states of the matter are the solid, liquid, and gas. And the fourth one is the plasma. So the solid can melt, it goes to the liquid, then it can evaporate, goes to the gas, and then gets ionization. The ionization process that creates the plasma. So the what contains in the plasma? It contains electrons, ions, atoms, molecules with nearly zero net electric charge. So this plasma is has been created by application of temperature or some other forms of energy from the gaseous state to the plasma state. So here you can see the formation of the plasma, the supply of the energy, which will ionize the gases, that becomes the radicals or the species presence. That's you can see the radicals present there. By application of heat or by some electrical energy, the gas gets ionized, and you can see the presence of the radicals here. That's the ionization of the gases. That creates the plasma. So coming to the diamond film growth, people have tried with the high pressure, high temperature technique and the chemical vapor deposition technique, which involves the plasma. In the high pressure, high temperature technique, which is almost similar to the process that how the natural diamond form, which needs high pressure and the high temperature. But the CVD techniques it's very much mankind, in which we need only a low temperature and the low pressure. We can get the high quality diamond as like the HPHT. So we focus for the CVD techniques. There are several CVD techniques has developed by the Russians as well as the US people, and one of them is the hot filament. But the drawback of the hot filament is that the filament needs to reach more than 2000 degrees Celsius, but the filament breaks at some time, so the growth will be not carried out uniformly. Then 1970s or 1980s, microwave plasma CVD comes by the Russian group, and also by the US people have developed the microwave plasma CVD. There we create the plasma using microwave. So the gases will get inlet to the chamber, then the microwave reacts with the gases, then dissociate the gases with its high frequency like 2.45 gigahertz. So the ionization of the gases presence there, it creates the plasma. Then the plasma contains those carbon species which converted into the sp3 hybridized carbon that can be coated as a thin film on the substrate. So this is the artificial diamond preparation using the chemical vapor deposition process. So there are various microwave plasma CVD process like the DC plasma jet, RF plasma. Based on the different sources, we can get the CVD process follows with the plasma based growth of diamond plant. So before going to the microwave plasma CVD synthesis, we need a substrate to grow the diamond. People for the electronics and the electrochemical applications, we need substrate should be also conducting. So people go with the silicon substrate because most of the electronic instruments are following the silicon substrate. So this is the silicon substrate commercially available. Then we dice into small pieces. So this is the diced silicon substrate. There we use some spin coating process to nucleate, because silicon contains no carbon. The spin coating suspension, which having the nano diamond colloids of having 5 to 10 nanometer of diamond particles, that will be spin coated on this silicon substrate. So this is the silicon substrate which is seeded by the nano diamond particles. Then these silicon substrates were placed in the microwave plasma CVD. This is available in the Hasselt University, Belgium. and this is the schematic diagram of the microwave plasma CVD. So this is the chamber, and these are the control panels for the microwave as well as the flow of gases and the control of the pressure. So once you open the chamber, it looks like this, and this is the sample stage here, which is covered by the quartz ring, and this is the chuck where we keep the nucleated silicon substrate here. So this silicon substrate will be placed inside this chamber. Then the chamber will be vacuum, so we unwanted gases will be removed. Once it reaches like 10 power more than 10 power minus 6 star, we can start passing our needed gases like methane, hydrogen, argon, nitrogen gases inside the chamber. Then microwave will be start, that will ionize the gases, that creates the plasma here. So this is the plasma which forms by the methane and the hydrogen gas. So you can see the substrate here, the silicon substrate, that's the diamond starts growing on the silicon substrate. Now after the growth of the silicon substrate, of diamond film on silicon substrate, how the diamond film looks, this is like a dark bluish color. This is the flat silicon substrate without growing any diamond. So these are the diamond film which grown on the silicon substrate. It's a very thick diamond, nearly more than a micron thick, so it's showing a color of dark bluish color. Depending on the thickness, the interference patterns occurs, the color also changes with the diamond film. So based on the input gases, we will get different colors of plasma. This is a very good plasma chemistry plays around here. So if you use 99% hydrogen and 1% methane, the gas is violet color. But when you increase the pressure, the plasma becomes pearl green. But when you remove the methane, when you remove the hydrogen, add only CO2, it becomes an orange and a combination of blue yellow plasma. And what happens if you add only the methane, it becomes like a bright green color, and only with CO2 it becomes blue and white. So depends on the gases what we are giving there, we will get different colors of the plasma. The different colors of the plasma results in the different species presence there, that will also creates different morphological diamonds. So you can see with the methane and the hydrogen, it forms microcrystalline diamond. MCD, we call it as a microcrystalline diamond. The reason is the grain size is more than 5 micrometer. And once you add some argon inside this methane hydrogen to the nanocrystalline, it becomes like very small grains, nearly around 50 to 100 nanometer. Then what happens if you remove the hydrogen and add only methane argon, that presence of ultra nanocrystalline diamond, which is developed by the Argon National Lab in US, patented by them. And this methane argon plasma having very plasma contains C2CH radicals, those creates ultra nanocrystalline diamond grains, and you can see the bright green color of UNCD plasma. So this UNCD plasma, UNCD films, which has a very smooth surface, and also the grains are really like 5 to 10 nanometer as compared to the microcrystalline diamond. These have a very smooth surface which is applicable for various applications like micro electromechanical systems, and we can also coat these UNCD on some probes, 3D structures, UNCD wafers, and also surface acoustic wave devices, and also uniform coatings on some bearings, and artificial retina project still ongoing in the Argon National Lab to make it the UNCD for the artificial retina and the field electron emitters. So I will focus on particularly the diamond applications for the field electron emission as well as the plasma illumination and electrochemical supercapacitors. So coming to the field electron emission plasma illumination, excuse me. Coming to the field electron emission, it's a very basic physics which deals with that emission of electrons from the surface of a material due to the high electric field. So it follows the two processes. One is the transmission of the electrons, that's a quantum tunneling happens through a potential barrier. The electrons will pass through the substrate. And second is the supply of the electrons or the bulk of the material to the emitting surface. So these two processes happens for the emission of electrons from this material through application of an electric field. So this is the basic field electron emission schematic diagram. This is the anode and a cathode. The sample is the diamond film, and the anode is a tip size of molybdenum having 2 mm dia, and this field electron emission process will be carried out in 10 power minus 6 torr. Should be in a high vacuum, so because of unwanted gases present there, which will not result in the better electron emission devices. These field electron emission devices are very much important for the vacuum based electron emission devices like FESEM, HRTEM, etc. So how to characterize the field electron emission material? There are some parameters, that is the current density, applied electric field, and the turn on field, as well as the field enhancement factor, and and also the work function. So these are the parameters which will help us to evaluate a field electron emission material. So there presence of your Folian Nottingham model, which is developed in 1928 by Folian or Nottingham. This is the equation for that, and from that they have made the ln J by E square to determine the turn on field as well as the field enhancement factor. So so once you apply the field, the current starts increasing. So the current density start increasing. At one point, there is a sharp increase in the current density, and this point that will present from the FN plot showing the low high field and the low field segments that presents the intersection of these 2 points makes the turn on field. So from there we can calculate the field enhancement factor. The field enhancement factor plays a key role, especially for the nanostructured materials because of the high aspect ratio. So where we can use these field electron emission based materials, the applications are, we can use as a cathode in a vacuum micro electronic devices, flat panel display, micro sensors, cold cathode, and recently we can coat on the AFM tips to make a scanning probe microscopy for surface imaging. So this is the one of the field electron emission devices developed by the Motorola, that you can see the flat panel display devices. But apart from these flat panel displays, there are several applications are coming to make some X-ray imaging. A Korean group is doing something with the X-ray imaging using the field electron emission based devices, and we can also generate a plasma that we are focusing as a plasma illumination device. So to be as a very good field electron emission material, there are some requirements. That's a low onset field, low surface work function, high robustness, long-lasting stability with a stable emission current, and it should be resistant to the ion bombardment. People have developed several materials, particularly carbon nanotubes, zinc oxide nanotube, nanorods, graphene, but these materials can have a very good turn-on field, low turn-on field with low surface work function. You can see the carbon nanotubes and graphene showing the turn-on field less than 1 volt per micrometer, but when you apply it to a high voltage or the longer lifetime, these materials cannot withstand the plasma environment or the bombardment part of the ions. So you can see that CNTs can degrade even at 400 volt, and carbon nanoflags were completely degraded or etched out by the electron emission even at 500 seconds. So we need a stable electron emission material. Then there comes the diamond film. But I mentioned before, diamond films is wide band gap and a high resistivity material. Then how we can apply this material for the electron emission? There are some specific properties of the diamond which really advantage the diamond to be as a very good field electron emission. Those are the chemically inert and small effective work function, which can lead to a robust performance with low threshold voltage. So we have compared the electron emission properties of UNCD and the microcrystalline diamond. Here you can see that the UNCD with smaller grains, which having a low turn-on field 19 as compared to the microcrystalline diamond material having a turn-on field of 65. So to know the reason why UNCD is better than the MCD, their TEM plays a key role in which the HRTEM result shows that the region 1 here, which is a UNCD material, in UNCD smaller grains of 5 nanometer size, which is surrounded by the amorphous carbon materials. So the amorphous carbon materials surrounding the MCD, surrounding the UNCD grains, which makes electron transport easily to make it a very good field electron emission material than the UNCD. So they derived a grain boundary conduction mechanism by Professor Yin and Lin in Taiwan, and they found that the MCD films having a very bigger grinds with lack of grind boundaries, so the electron emission is very much limited. But when you come to the UNCD, it has very smaller grinds, aspect ratio is more, which will be surrounded by abundant grind boundaries, which makes the UNCD highly conducting and which makes UNCD having a better electron emission material. But there is also a drawback that the UNCD materials are having amorphous carbon, which is also not electrically conducting much, so that hinders the transport of the electrons. Then we place the role of incorporation of the nitrogen in the plasma, then remove the argon and put the nitrogen there, which will make what happens to the morphology. There you can see the UNCD grown in the methane and argon having very smaller grinds, but the nitrogen incorporated UNCD having a wire-like structures, which makes a high aspect ratio material than the UNCD. We measure the field electron emission properties. There you show that in UNCD, the nitrogen incorporated one having the lowest turn-on as compared to the UNCD and with a high current density. To know the reason, we carried out a localized field electron emission called a scanning tunneling microscopy and scanning tunneling spectroscopy. There from the current imaging tunneling spectroscopy carried out IGCAR Kalpakam, which shows that the grinds are insulating in nature, but the grind boundaries are electrically conducting, that having a band gap of metallic in nature. So what is present in the grind boundaries? And to identify that, HRTM helps us to know that. You can see the colored HRTM, which clearly shows that the green regions are the graphite phases, which is encasing the nanowire of diamond. So each nanowire is encased by the graphene structures, which makes it the 9 UNCD films electrically conducting, that helps for the efficient electron transport with one-dimensional nanostructures, increases the aspect ratio with high field enhancement factor, that gives NUNCD films as a better electron emission material with highly electrically conducting in nature because of the presence of nanographite at the grind boundaries. So far I have shown only the as a film base, as like a flat material. But what happens when you make a nanostructure in the diamond? But diamond is a very strong material. Can we make nanostructures? Yes, it's possible. That we have utilized the reactive ion etching process. We have masked the NUNCD films using diamond nanoparticles of 5 to 10 nanometer. Then we use oxygen and CF4 plasma to reactive ion etching, that creates the one-dimensional nanostructures of NUNCD nanorods. Then the field electron emission studies were carried out, which makes a further improvement in the field electron emission with low turn-on field and high current density and with better field electron emission pattern. Now we have shown only the NUNCD nanorods, but can we pattern it to further improve? We have followed a basic lithography process that creates the NUNCD nanorods in a patterned way, and you can see these are the NUNCD nanorods, and the same image just shows that each nanorod having a hybrid of a graphene and diamond, which makes the nanorods hybrid, the diamond nanorods having a low turn-on field with high aspect ratio with a high field enhancement factor. So the sp2 graphitic phases in the grind boundaries is the key role for the enhancement of the field electron emission. You can find more information in this book chapters as well as in the review article based on this nitrogen incorporated UNCD films written by me and my professor from Belgium. And now coming to the electrochemical supercapacitors. As we all know that there is a we need a very good energy material compared to the battery. The supercapacitors having a very good power density is the energy density. So we have India has also developed a supernova sports car here. So compared to the other carbon-based material, the boron doped diamond, we have talked about the nitrogen incorporated diamond. Here I talk about the boron doped diamond because it's a p-type. That is especially for the electrochemical supercapacitors having a very good potential window. But nitrogen incorporated diamond, which having a n-type, so it goes for the electronic applications. So if you see the boron doped diamond having a very good potential window, low background current, high sensitivity and high electrochemical stability, which as compared to the other carbon-based materials, which makes the diamond with the boron doped diamond as a very good electrochemical supercapacitor electrode. So what we have developed is that here also we have incorporated some nitrogen in the plasma. There creates a nitrogen and boron plasma that makes a boron dope diamond nanowalls. You can see a very one-dimensional nanowalls presence here, which shows the presence of sp2 graphitic phases encasing the nanowalls, which also a key factor with making us a core and a shell. Diamond as the core and the graphene as the shell, that makes a very good electrochemical supercapacitors. As you can see here, the capacitive current enhances with increasing the scan rates, as well as from the galvanostatic charge discharge studies, it's a linear and a symmetric curve which happens, which having very good charging and discharging, and you can see the remarkable retention of 97.6 after 10,000 cycles, which shows the outstanding stability of these BDD electrodes. Then another process we went to make hybrid with the diamond, that we make some carbon nanographs with the boron dope diamond. Those using a single step process of the microwave CVD. There we have forms a boron dope diamond with graphitic grind boundaries and with the carbon nanographs decorated with the nanoparticles of the diamond, which helps for a very good super capacitor electrode with 10,000 cycles of having a 95% outstanding stability. So this electrode is much better as compared to the other published electrode, as I have shown here. Compared to the other carbon based electrodes, this hybrid electrode with the diamond and carbon nanographs having a very good capacitance behavior with in two electrolytes, in sodium Na2SO4 as well as with the FeCN6. So as a summary of my work, we have fabricated the nitrogen incorporated UNCD films, particularly for the electronic application, electronic applications like the plasma illumination devices. Then we have fabricated boron dope hybrid diamond with the diamond as the core and the graphene as well as the carbon nanographs as the cell, which makes the diamond as a very good exceptional electrochemical stability, which shows that these diamond electrodes are diamond cathodes having a very good advantages in applications like electronics as well as the electrochemical supercapacitors applications. So more information you can find from this book chapter that we have written about the comparison of the graphite and the diamond. It is very basic for the people to understand about what is graphite and what is diamond, how the evolution of the diamond and the change in the graphite to the diamond to graphite happens, and the characterization techniques. Those are all involved in this book chapter. So now I thank you all for your kind attention. So if you have any queries, please let me know. And one information to the audience that IMMT having a dissertation program for 6 months, Jan to June and July to December. You can see in the IMMT website for those dissertation program. And also we have an internship program for the master students. Those will be in May, June, July, 2 months program, 8 weeks totally. So you can apply, and the call for the internship will come soon. So welcome you all to IMMT, and looking forward for a fruitful collaborations. So finally, thank you all for your kind attention. So any questions?
Yeah, we have posted in the paper, sir.
Yes, sir. I'll go through there.
Yes, sir.
So what will be the magnetic properties of diamonds? Sir, I didn't go through any studies, but there is superconductivity behavior is there for the boron dope diamond. You can see some works from the from UK group has did with the superconductivity of diamond. So please refer to those papers. I'm not in this area, but people have did some work on it.
Any other questions?
Yes,
There
sir.
is no questions in the paper, sir.
Prasadaman, sir.
Okay, sir.
Yes, sir. I am on the online, sir.
Yes, sir. Sir, some question in the chat box, sir.
Sir, there is a mechanism. Do you mean the mechanism of the diamond growth? If it is though, that mechanism is like we need to do the optical emission spectroscopy studies to derive the mechanism of the microwave plasma CVD growth of MCD, UNCD, NUNCD as well as the boron dope diamond. Based on the energetic species present in the plasma, we could able to derive the mechanism of this diamond. I didn't show most those contains more plasma chemistry, so I didn't involve here. If you refer to my my publications, you could be able to know the optical emission spectroscopy effect to determine the growth structure of these diamond films. So,
Okay, sir.
Sir, please 3 minutes, sir.
Okay, sir. Can I deliver the vote of thanks, sir?
Yeah, please, sir. Please 3 minutes, sir.
Sir?
Sir, please wait, sir.
Wait for 2 minutes, sir.
He is on the one phone call, I think so. Please, we have to wait, sir.
Few more questions are in the chat box, sir.
yes, sir. Sorry, sir. I was in a call. What about the conducting property of diamond when compared to the 2D materials? Sir, if you go for the 2D materials, diamond conducting property is not that much good enough. People are still looking to develop the highly conducting, but the stability as compared to the 2D, diamond is the best. And can you tune the band gap? Yes, we can tune it by doping with the phosphorus, nitrogen, and the boron. The band gap can be tuned. We have the UPS measurements can show the band gap. For the boron dope, it was reported like 3 eV, and nitrogen we got up to 3.5 eV. So we can able to do that. And any specific method to alter grain size and boundaries? Yes, sir. I have mentioned from the microwave plasma only by the change in the gaseous species, like methane, hydrogen will show the MCD. If you add some argon in the plasma, reduces the grain size. And if you remove the argon, addition of the nitrogen, again making nanostructured grains. And only with methane, hydrogen, nitrogen also makes ultra nanocrystalline diamond grains. So there is plenty of papers available with the alteration of the grain size and the boundaries. Can we able to make a single layer or few layer of diamond? If yes, means what about the ATM stability? So that is very much complicated to go for the single layer or few layer. That it is not possible in microwave CVD because the interface between the diamond layer with the silicon, it contains some amorphous phases will be there, like 5 to 10 nanometer will be the amorphous carbon. So it is very much difficult to get a single layer or few layer of diamond. Either you can make some freestanding diamond film etching out the silicon, but that is also a complicated process. So it is not easy to make a single layer or few layer of diamond. Thank you, sir. Yes.
Now I invite Dr. Purushothaman sir to deliver out of thanks, sir.
Okay, sir. Right, sir. Good morning to everyone. It's my privilege to have been asked to propose a vote of thanks at this juncture. I would like to express my sincere thanks to the management, SRM group of institution, for supporting us to organize these type of events regularly. On the behalf of the Department of Physics, SRM TRF Engineering College, Trichy, I express my sincere thanks to our Chief Guest Resource Person, Dr. K.J. Sankaran, Senior Scientist, CSIR, Bhubaneswar, India, for accepting our invitation towards this FTP and for his valuable and informative talks on diamond electrodes for electronics and energy applications. I hope that your information shared today, which is very useful for all the participants, sir. Thank you, sir. I would like to extend my special thanks to our higher officials of SRM TRP Engineering College, Director, sir, Principal, sir, Dean Research, sir, VP, sir, all HODs, and the faculty members. Also, I extend my sincere thanks to our organizing team to make this event as a grand success one. At last but not least, I express my heartfelt thanks to the participants, research scholar, and the faculties of various colleges for made this program as a colorful event. Once again, I thank one and all. Thank you, sir.
Thank you so much, sir, for your kind,
Thank you.
introduction. Yes,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir. Yes, sir. So, sir, now I leave, sir.
Yes, sir. Thank you, sir.
Okay, sir. Thank you, sir. Yes, sir.
Dear participant, the feedback link will be posted in this GeoMeet. Thank you.
Participants, another talk will be at 4 o'clock, entitled by a new educational policy by Dr. Alok Kumar Gupta. Kindly attend the meeting by on time. To avoid the network issues, kindly
Good day,
join
sir.
before 10 minutes or reach earlier. Thank you so much for your kind cooperation in this regard.